The classic water-hammer theory is based on a set of assumptions that limit its range of applicability to standard designs. However, phenomena not accounted for may affect the transient wave propagation in a way that designs might be underestimated. That's why it's important to understand and identify the most relevant phenomena that affect the water-hammer wave: attenuation, shape, and timing. This is the goal of this session. First, I will give a brief historical background of water-hammer theory, how it was built. Then we will focus on the physics of the phenomena affecting pressure waves. And finally, I will explain the main research approaches to tackle these problems. On this slide, I will briefly present the history of water-hammer theory, but focusing on the phenomena, not only on the chronology. Science is the result of a stepwise aggregation of research contributions. So, when talking about history of science in a specific field, like hydraulic transients, it is important to highlight the contributions of those key researchers that built up the theory, with their associated assumptions that were taken at that moment. To support this, I will make use, additionally, of numerical output from the classic water-hammer model. The origin of water-hammer theory is very much linked with the field of acoustics. Both they started with Newton and Lagrange, which studied the propagation of pressure waves in fluids. For instance, they determined the airspeed, the sound speed. A water-hammer wave is a very special pressure wave, and its celerity can be measured and computed in a similar way to acoustic waves. Then, already on the 20th century, Joukowsky proposed his famous equation that allows the calculation of the associated pressures during a transient phenomenon. Hence, as model output, we get a constant pressure value. Then Korteweg continued Newton and Lagrange's work in wave celerity, but now considering also the pipe wall elasticity. So the wave celerity and the associated pressure rise computation were refined. Thanks to the contributions like Aliavis assumptions, like slow maneuvers could be considered, and numerical schemes like the method of characteristics could be implemented. So now the model output is not just a constant value, but the whole pressure history of the transient event, considering the wave propagation through the pipe. Finally, Weisbach and Darcy and other researchers contributed to the description of the water-hammer wave dissipation, considering friction. So these are briefly the basic research contributions and their assumptions beneath the classic water-hammer model. To summarize these assumptions, so concerning the fluid, 1D flow, quasi-incompressible fluid, which is constant fluid density, and one-phase flow, which means no mixed air is considered, and concerning the pipe, linear elastic behavior of the pipe wall deformation, and pipe geometry is uniform, hence there are no reductions or expansions, junctions, etc. In terms of the wave, dissipation, quasi-steady head losses, the fluid is considered adiabatic, and there is no mechanical damping, hence the pipe deformation and movement does not generate additional energy dissipation. These assumptions are good enough to solve most of the hydraulic design problems. However, depending on the pipe system, sometimes the classic theory is not enough, and we may need to include additional assumptions. For instance, if transient pressures go below vapor pressure, then we may consider cavitation. If there is trapped air, the transient response will be also very different. Leakages and blockages can be modeled, so water-hammer theory can be used for their detection. The movement of the pipe during a transient event also changes the wave shape and timing, like the pipe wall viscoelasticity. And if we consider unsteady friction, then wave dissipation might be higher than considering just steady friction. In the following slides, we will cover one by one this missing phenomenon. So let's start by unsteady friction. What does exactly mean? In real world, pipe flow is not 1D. If you have a look at at the top right picture, when a valve is rapidly closed, not the whole water column stops homogeneously. As you can see from the velocity profile depicted at the left of the figure, during the steady state, the momentum of the fluid close to the pipe axis is higher than the one close to the pipe wall. Hence, close to the pipe wall, there might be a faster inversion of the velocity gradient. Consequently, during the transient state, we can get a situation like the one depicted in the velocity profile shown at the middle of the figure, in which the velocities close to the pipe wall are already inverted, but not the velocities close to the pipe axis, and the cross-sectional average velocity could be still positive. In this case, the shear stress would be contributing to the fluid motion. And steady friction models intend to compute friction taking into account this phenomenon. There are plenty of alternative models with different assumptions to compute unsteady friction. The plot below is an example of one of its outputs. As you can see, wave shape and dissipation rate are different. Friction dissipation seems to be underestimated in the classical approach. The phenomena concerning the pipe wall rheological behavior has to do with the viscoelasticity of the pipe wall. Plastics like polyethylene or PVC don't have exactly an elastic behavior, like the one assumed in the classic water-hammer theory. They are rather viscoelastic. This means that their deformation is delayed, retarded, with respect to the rapid loading caused by the transient pressure. The left plot depicts this phenomenon. In the horizontal axis, there is the pipe wall deformation, and in the vertical axis, the loading of the pressure. In black color for a metallic pipe, copper in this case, and in gray color for polyethylene. As you can see, the gray line presents a different curve for loading and for unloading. This is due to the retarded response of the material. This phenomena is also called hysteresis and results in a very different response of the piping system during transient conditions, as depicted in the right plot, where pressure histories are compared to the same transient event. In viscoelastic pipes, there is therefore mechanical damping, and the water hammer wave dissipates much more rapidly. Related also with the pipe wall movement, there is the fluid structure interaction phenomenon, which is also a frequent issue in pipe designs. Transient pressures make the pipe move, and when the movement is important, it will affect as well the inner pressure. So there is dynamic interaction between the inner fluid and the pipe structure. The pipe might move in several degrees of freedom or pipe variation modes, so the fluid structure interaction problem gets easily complex. The plot below is an output of a numerical model considering fluid structure interaction for axial movement of the pipe wall. As you can see, pressures can be much higher than the ones expected from Joukowsky equation. Water hammer models can be used also to detect leakages in pipes. The principle is that a leak results in a partial reflection of a water hammer wave. If this reflection is identified in the pressure wave history, then the traveling time of the reflected wave can be guessed, and if the wave celerity is known, then the exact location of the leakage can be computed. The plot shows data from some experimental tests in which the leak size is modified and, therefore, the intensity of the associated wave reflection. Concerning air entrapment, the presence of air affects a lot the propagation of the water hammer waves. The velocity of the wave is highly reduced with the presence of air. In principle, this is positive. Lower wave celerities imply lower transient pressures. However, if the air is not homogeneously mixed, but rather allocated as a pocket in a specific point of the pipe system, then reflections of the water hammer wave may be generated, and consequently, higher pressures than the one computed by Joukowsky may occur. When pressure in the pipe is below vapor pressure, then there might be cavitation. If it is strong enough, we can have column separation, which means the cavitation void is large enough to separate the water column. When these water columns collapse, then we can have very high pressure spikes. This is quite a common reason of pipe bursts in piping systems. Nowadays, there is active research to improve the classic water hammer model. One of the approaches is based on the development of add-ons to the basic model in order to increase its accuracy for a special purpose, like the inclusion of all the phenomena discussed in the previous slides. So, if you know in advance that some of these phenomena might be relevant for a specific piping system of study, then you may consider them by adjusting the assumptions beneath the basic model. Computational fluid dynamics is also another active field of research. With CFD, you can model anything. For instance, this plot is the result of a CFD simulation in which the air vessel with a valve in its outlet and a certain flow through the pipe during the steady state. Then the valve is closed. The associated downsource propagates towards the downstream boundary, where a water drop is generated. As you can see, complex phenomena can be simulated by means of CFD. The drawback, though, is the computational effort required. Experimental research is also very useful, not only to explore new phenomena, but also to validate existing hydraulic models. Some time ago, I had the chance to work with these 3 different experimental facilities, composed of different pipe materials and geometries. The first, a short straight copper pipe, and the second, a copper coil, and finally the last, a polyethylene coil. So I was able to compare the different transient behaviors caused by the different configurations. For such comparison, I normalized the respective measurements and I took as reference this gray line, which is the ideal water hammer wave. These are the measurements of the straight copper pipe with a strong fluid structure interaction effect because the pipe could move axially. These are the pressures at the copper coil, also with a kind of fluid structure interaction due to the coil movement. And these finally are the measurements at the polyethylene pipe with the effect of the viscoelasticity of the pipe wall, so different wave shape and higher damping is depicted. As you can see, very different responses from the different pipe rigs, and therefore this phenomena, not accounted in classic computations, is actually relevant and important when trying to describe well the water hammer wave propagation. To summarize, the classic water hammer model is a good approximation. However, transient pressures might be underestimated in presence of phenomena like cavitation, trapped air, leakages, fluid structure interaction, etc., which affect the pressure wave attenuation, shape, and timing. To cope with these problems, I have briefly shown the main research approaches, which are extending the basic model by means of add-ons, computational fluid dynamics that enables the simulation of complex systems, and finally, experimental research, which is very useful for the validation of these models. Finally, I would like to finish with this message. Engineers should be able to identify and evaluate the influence of these mechanisms, because first, these are usually not included in standard water hammer software packages, and secondly, these are often hidden in practical systems. So keep this in mind when designing your piping systems. Thank you very much for your attention.